Hi everyone, let's move on and talk about quadratic functions. We've been studying graphing techniques, so we know how to shift, stretch, and reflect most basic algebraic curves. And you can see some of those in the figure on the left-hand side of the screen. So graphs of y equals 1/3 x squared, y equals negative 9x squared, y equals negative 1/2 x squared. And we can see that relative to each other to remind ourselves that if you have a coefficient in front of the square term, that coefficient affects whether the graph is stretched or compressed vertically. And then if you also have a negative sign in front, then that affects whether or not the graph has been reflected across the x-axis. So you can see these graphs all on the page pass the vertical line test, so enhancing our concept here, which is studying functions. So we basically only have parabolas that open upwards or downwards. You can see in the second figure that if you shift y equals x squared to the right 4 units, then your vertex is moved to the right 4 units. And then likewise, if you shift down 5 units, your new vertex is the ordered pair 4, 5. Or excuse me, 4, negative 5. Now, one thing I would like you to notice in the order of operations here, if I were to insert an additional graph where I had affected the graph with a vertical stretch, let's say. Now I'm just freehanding this. Let's say we have y equals 2 times x minus 4 squared. The graph of y equals x minus 4 quantity squared left off with its vertex at 4, 0. You can see the 2 would maintain the vertex at 4, 0. So in effect, what we see is the translations or operations on functions, if you will, that most affect the vertex are the horizontal and vertical shifting. So in this particular case, your vertex, y equals a number times x minus h quantity squared plus k, is going to be right h and up k. So we can actually look at the equation if it's in this form, which by the way is called standard form, and read off the vertex. Okay. All right, and the third picture on to the farthest to the right shows that if a parabola opens upward, then you must have a lowest point on the graph, and in doing so you would have a point whose y-coordinate would be the smallest y-coordinate possible. That particular value is what we refer to as the minimum value. If your parabola does not open upward, and if instead it opens downward, then you have a highest point on the graph, or rather a largest y-coordinate, which is still the y-coordinate of the vertex, and that's what we refer to as the maximum value. Now remember, the vertex is an ordered pair, a value is a number. So anytime we refer to the value of a function, we're talking about a y value. Notice also that parabolas have nice symmetry, and the axis of symmetry is the vertical line passing through the vertex, so therefore it would always have equation x equals the x coordinate of the vertex. Okay, so now if your parabola opens upward, then tying into our coefficients over here, we would have a positive leading coefficient in the equation. If it opens downward, it means it's been reflected across the x-axis. We'd have a negative leading coefficient, as was the case for these two guys. Okay, and if you can find the vertex and you know which way your graph opens, then the range of the graph, if the parabola opens upward, is from the y-coordinate of the vertex to infinity, whereas if it opens downward, it's from minus infinity up to the y-coordinate of the vertex. Okay, continuing here to look at some specific graphs. So basically, if I take the graph of y equals x squared and I shift it right 1 unit, and then I stretch it, or rather compress it vertically by a value of 1/2, notice that the vertical compression didn't change where the vertex is. If I additionally reflect it about the x-axis, it wouldn't change where the vertex is. And then when I move it up 2, that's your next change in the vertex. So basically, again, if you're given standard form, then we can simply read the vertex very confidently, right 1 and up 2. Okay, so that's our vertex. Now the question is, what happens when you have a formula for the parabola that's in general form, such as this one, where it's not all nice and collected for graphing techniques? So when you have something like ax squared plus bx plus c, what do? I mean, now here's something that's consistent. If I were to expand my standard form's binomial, I would see that the position of the leading coefficient is consistent. So for f of x equals 2x squared minus 4x minus 1, that guy is still going to open upward, so we can be confident of that. And then if we can find the vertex and we know which way it opens, we can identify the range, the minimum value, the axis of symmetry, and all of those good features. Okay, so I would like to show you in an additional video how to take the guy that we're looking at and transform the equation into standard form so that we can most easily read the vertex. But again, to recap, if you can know which way your parabola opens, you'll know that by the leading coefficient. And also, if you can find the vertex, then you can easily find the range, the axis of symmetry, and maximum or minimum values. Okay, so stay tuned for the next video.